Okay folks, here we go again. So this is the go through for the electricity multiple choice questions. And we're starting off with the power dissipated P going with the current I in a component that obeys Ohm's law. So they've told you it obeys Ohm's law because that tells you it's going to have a constant resistance. So we'll remember P equals VI, but we can't just use that equation because the V will change. But the thing we know staying the same is the resistance, so we want to use P equals I squared R. So this means that the power is proportional to the square of the current. So really again you've got like a 50-50 chance with very little understanding at all here, because in this one and this one the power goes down as the current increases, so it's got to be one of these two. You might fall into the trap of saying P is proportional to I if you don't realise that the V is changing, but this is the one you want. P is proportional to I squared. So that is graph A. Okay, question 2. There's quite a lot to think about here. So we've got 1.8 volts. This is very much one of those sort of questions where it really helps you if you put the information on a diagram. 1.8 volts across the LED. The current is 20 milliamps. So let's put that on here, 20 milliamps. We need to know the value of this resistor here, R. So you need to look at this and think, well, I don't know the potential difference across here, but I do know the current going through it. Can I work out the potential difference? Well, I could work out the potential difference here. So if I connected my sort of imaginary voltmeter there, I could say V equals IR 20 milliamps times 10 ohms gives me 0.2 volts. So this potential difference here is 0.2 volts. This one's 1.8 volts, but if we add those two together and this one, they must add up to 5. So that's 2. So we're left with 3 volts here. Now if you look at the information we've got the potential difference across here and we've got the current, so we can say R equals V over I, which is 3 over 20 times 10 to the minus 3, which comes to 150 ohms. So the answer is C. Okay, question 3. So a mobile phone operates at a constant power of 200 milliwatts, 3.7 volt a battery, which has a charge capacity of 9,400 coulombs. So the time to discharge, probably the easiest way I think to understand this is we've got P equals V times I. So we know the power and we know the voltage, so we can do that the current is P over V, which is 200 milliwatts, so 200 times 10 to the minus 3 over 3.7, and that gives you a current of 5.4 times 10 to the minus 2 amps. Then you can do Q equals IT, which means the time for this amount of charge to pass with this current will be Q over I, which is our 9,400 coulombs divided by our 5.4 times 10 to the minus 2 amps, and that comes to 174,000 seconds. But they've given us the answers in hours, so we need to divide that by 60 to turn it into minutes, and then 60 again to turn it into hours, and if you do that you get 48 hours. So the answer is B. Okay, question 4. Just move that a little bit so you can see. So which graph shows the variation of the resistance with temperature for an NTC thermistor? These are the only thermistors they talk about. NTC stands for negative temperature coefficient. What that means is that when the temperature goes up, the resistance goes down, a negative coefficient. So not this one, not this one, because these are both going up, 2 that are going down. I always think the clue with this sort of graph is if it's going down like this, sooner or later it's going to go through the axis, and somehow this thermistor will have a negative resistance, so that can't be true. So the answer for this one is C. What I would say there is that that is actually an exponential decrease, a bit like half-life, and we will look at that in a little bit more detail later on. Okay, question 5. So the figure shows an LDR and a fixed resistor are connected in series across a cell. The internal resistance of the cell is negligible. So this is a classic potential divider circuit, and we're trying to work out the ammeter and voltmeter readings when the light incident on the LDR is increased. So the first thing you have to know is the fact that when you increase the light intensity, the resistance goes down. So if we just put this on the diagram here, the resistance of this part goes down. If you don't know that fact, it doesn't matter how good your understanding is, you're not going to get the right answer. But once you've got that fact, what you need to do is to go through these steps. It's very tempting to think the resistance goes down, remember V equals IR, and think therefore the voltage will go down here because there's less resistance. But you need to think of it more carefully, because when the resistance here goes down, the current's not going to stay the same. So the resistance goes down, the current goes up, you don't really know what's going to happen. So this is the process that you have to go through. So the resistance of the LDR, we know that goes down. That means the total resistance of the circuit will go down, because that's the total of these two, and this one's not changing. What that means is the current in the circuit will go up. Okay, so straight away over here we know it's not A and it's not B, because the current is going to be increasing. Then you've got to think about what's going on here. Well, there is more current in the circuit. If there is more current in the circuit, then this voltage here, this potential difference here, will increase, because the current has increased and the resistance has stayed the same. If that voltage increases, these two always have to add up to that one, so that voltage must decrease. So the current increases, but the voltage across here decreases. So the answer to question 5 is D. Okay, question 6. So a battery of negligible internal resistance and an EMF of 12 volts is connected in series with a heating element. The heating element has resistance of 6.5 ohms. Okay, what is the energy transferred in 5 minutes? So this is a nice straightforward question, where what we do is we say that P equals VI. We haven't got a current. You could work out the current from V equals IR, or you could do V squared over R. That's 12 squared over 6.5, and that gives you a power of 22.1 watts. Then you can do energy equals power times time, 22.1 watts. We've got 5 minutes. Okay, so they've put you the answer 111 in here, just in case you fall into that trap with 5, but of course you won't fall into that trap. 5 times 60, 300 seconds, and that gives you 6646 joules. So 6650, 3 significant figures, is your answer. Okay, question 7. Quite a lot to look at here. So we've got 3 cells. Each one is 1.5 volts and has an internal resistance of 0.6 ohms. Which combination will give you a total EMF of 1.5 and a maximum current of 7.5? Well, for a bit of practice, let's work them all out. In this one, if we connected a voltmeter between there and there, all of the cells are in the same direction. So we've got 3 lots of 1.5 volts. So we've got 4.5 volts in total. The resistances are all added together, so we've got 1.8 ohms in total. And then we've got a maximum possible current. If you just short-circuited that, the current you would get would be I equals V over R, which is 4.5 over 1.8 which is 2.5 amps. Okay, that clearly doesn't meet either of these two criteria, so not that one. If you look at the second one, you've got to notice the difference here is this one's the wrong way around. So you've got 1.5 minus 1.5 plus 1.5, so you've got 1.5 volts, so we have hit that criterion, but the total resistance is still 1.8 ohms. So you're only going to get about 0.8 amps from there, but you are going to get an EMF of 1.5 volts. If you look at this one, life's getting quite complicated. This is 1.5 volts, these are both 1.5 volts as well, it's all facing the same way. So the potential difference between there and there is 1.5, so this is giving you 3 volts. You can go through that and work out that this is 0.6, this is 2 0.6 in parallel, which means it gives you a total of 0.3 ohms. So the total resistance of that circuit is 0.9 ohms. So that gives you just over 3 amps as the maximum current. Okay, here's our, so none of them have worked so far, but here's our last one, 1.5, 1.5 or 1.5, because these are all in parallel. The way you need to think about this is if you're an electron here and you go through one of these 3 cells, that will give you 1.5 volts. But the total resistance of this circuit is, you've got 0.6, 0.6 and 0.6. So this is 1 over 0.6 plus 1 over 0.6 plus 1 over 0.6 equals 1 over R. That makes R equal to 0.2 ohms, which means you can get a current of 7.5 amps. Okay, I'm sure if you're good at those you can find a quicker way of doing that, but I thought I would just talk you through them all just to give you some practice at looking at them. Okay, question 8. Which statement about superconductors is correct? When a metal becomes a superconductor, its resistivity is almost 0. So the thing that's killing you here is it's not almost 0, it's just 0. If you took that word out, it would be correct, but that word's there, so it's not. The temperature at which a material becomes a superconductor is called a critical temperature. That is true. Let's just check the other one. So when current passes through a superconductor, the PD across it becomes a maximum. Okay, so that's rubbish. There is no PD across it because there is no resistance. And if you think copper is a superconductor at room temperature, you really haven't been paying attention. Okay, question 9. What is the equivalent to the ohm? When you get this kind of question, what you must do is just to think of an equation. So you know, for example, R equals V over I, and then you think, well, that's not there because it doesn't say volts per amp, which could be there, but volts is joules per coulomb, so it's joules per coulomb. I'll write it this way, divided by current is, current is coulombs per second. So by the time you take this at the top, you get joules per coulomb squared second, which is B. Okay, number 10. So a circuit consists of a cell, a thermistor, a fixed resistor and 2 ammeters. So thermistor here, fixed resistor here, ammeter measuring the current through each, but they're in parallel. We've got a constant EMF and a negligible internal resistance, and we look at the 2 ammeters. Which row describes what happens to the current in each ammeter when the temperature of the thermistor decreases? Okay, so again, what you have to remember, a fact that you have to know, is that if the temperature is decreasing, the resistance of the thermistor here is increasing. Okay, so the other thing you need to know is that if we look at A2 down here, it makes no difference. You could take this part of the circuit out altogether, the current around here wouldn't change because it's got the same EMF being applied to it. So in A2, the current is not going to change, so it's not B or C, but in A1, the resistance, the temperature's gone down, the resistance has gone up, therefore the current's gone down, so A1 will decrease. So 10 is A. Number 11. So a voltmeter is used to measure potential difference. Which row gives the position and ideal resistance? So remember, here's your component. To measure the potential difference, we've got to be connected either side of it, because it's a difference. You've got to know what it is when it goes in, what it is when it comes out, and you measure the difference. The key thing about instruments for measuring always is that you mustn't actually change. You always change something when you measure it. You can't help doing that, but the smaller you can make that change, the better. So we don't want the resistance of this circuit to change just because I've put a voltmeter in, because if it does, you won't be getting the voltage that was there before you tried to measure it. So how can we not change the resistance? Well, we'd like the voltmeter to have an infinite resistance, so when I put it in parallel, it makes no difference. So we've got to connect it in parallel. Again, if you didn't put C or D, I'm really scared for you. So C or D, it's got to be in parallel, and the ideal resistance is infinite. So 11 is a C. Okay, this question's slightly confusingly laid out, I think. So care is, as much as anything here, important. So two resistors are both shown uniform cylinders, equal length, made from the same conducting putty. The diameter of Y is twice that of X. So if this is D, this is 2D. Okay, so the crucial thing to understand there is, because it's pi r squared or pi d squared over 4, if this has got a cross-sectional area of A, this has got a cross-sectional area of 4A. The diameter of D is twice that, so the resistance of Y is R. So they told you this one is R, and what you need to be able to see is if that's R, because it's R equals rho L over A, this one is a quarter of the area, so a quarter of the area means 4 times the resistance. So this one is 4R. The total resistance of the combination is 4R plus R, makes 5R. Okay, number 13. So the circuit has two identical cells. Now this looks like quite a complicated circuit, but it's not actually as difficult as it looks. We've just connected a voltmeter across these cells, and we've got one resistor and an ammeter. So each cell is 3 volts, so 3 volts, 3 volts. The resistor is 12 ohms. No internal resistance. So which row shows the correct values? So the key thing to understand here is, if you're measuring the potential difference between there and there, every electron, whichever way it went, has only gained 3 volts. So this is going to be 3 volts. We're then applying 3 volts across a 12 ohm resistor. So we do I equals V over R is 3 over 12 is 0.25 amps. So 0.25 amps comes around here. So 13 is A. Okay, 14. Bit of work to do on the calculation here. So a doubly charged ion. So the first thing you have to understand is that the doubly charged ion means it's a 2+ ion. So whatever element it is, it's something which is 2+, or possibly 2-, but definitely 2. What does that mean? Well, it means the charge is 2 lots of 1.6 times 10 to the minus 19, which is 3.2 times 10 to the minus 19 coulombs. So for every ion that goes past, we get 3.2 times 10 to the minus 19 coulombs of charge. The current's 0.64 amps, so we do Q equals IT. 0.64 times 1 minute is 60 seconds. That gives you 38.4 coulombs of charge. But we've got to work out how many ions there are. So what we need to understand, sort of invent yourself an equation here, the total charge. I think it does help to write this out if you're not totally confident with this sort of thing. The total charge, that's an E, isn't it? That one's a G. The total charge is the number of ions times the charge per ion. So what that means is that the number is the total charge, which is 38.4, divided by the charge on each one, which is 3.2 times 10 to the minus 19, and that gives you 1.2 times 10 to the 20 ions going past. And question 15, one more circuit to go. So the circuit shows a cell with negligible internal resistance connected to a circuit with 3 resistors and an ammeter. And the key thing to notice here is there's a voltmeter in the circuit, but it's not where you'd normally connect it across here, it's in series. So which row shows the readings on the ammeter and the voltmeter? So this part of the circuit is 20 ohms, but this part of the circuit, because this voltmeter will have an infinite resistance, this part has got an infinite resistance. So the total circuit resistance here is 20 ohms. So the ammeter is going to read I equals V over R equals 1.5 over 20 is 0.75 amps. Sorry, I beg your pardon, 0.075 amps. So that makes it not C and not D. Then you need to understand that this way, why is there no current flowing? Because this has got an infinite resistance. So the PD across here is 0 volts because there's no current flowing through it. All of the PD is across here, the 1.5 volts. So that gives you the answer for 15 as B.